There it is.
Okay.
Got it.
Okay. Whoops, where's the meeting? Okay, got it. Okay, well, we're on the air now, finally, after a slight delay. I apologize for the 12-minute delay with some technical issues with my computer. So welcome to the first Friday meeting of the SBAU Astronomy Club at the museum for October, what's the date? 7th.
7th.
And we most of the business stuff, we're having a business meeting tomorrow night, so that'll all wait for that. We'll get to a list of our future this month upcoming outreach from Chuck. He will give you the highlights of our month ahead. So go ahead.
Okay, well, tomorrow night is the monthly public star party at the museum, second Saturday of every month. We'll be starting the star party at 7:30. And for club members, we have the planning meeting starting at 5:30 in the little circle outside of the observatory. Then on the 15th, Saturday, we're doing a couple of hundred Girl Scouts at Camp Arnaz up by Ojai. Chrissy's going to be there. And then on the 20th, we're doing Hope School for fifth graders for a planet night. Then on the 21st, the third Friday of every month, it's Westmont Public Telescope Night. But unfortunately, that's the same night that our annual camp out starts. So on the 21st, 22nd, leaving on the 23rd, we have our annual camp out at Kachuma Lake in the Mohawk Shores area. And I've asked people to respond to me if they're coming and if they want to partake in the catered dinner or potluck or whatever, and I'll have those statistics for Jerry tomorrow, and that's when we'll make our decision on whether we're going to do the catered dinner. But if you can go to Westmont, if you're not going camping, please go to Westmont and support them. And then on the 27th, on Thursday, Monte Vista School, we're doing a planet night for them too, for their fifth graders. And we also have a couple of El Capitan Canyon events, but those are limited attendance because we have to go through all kinds of security stuff with their people. So that's the outreach for this month.
Okay, thank you, Chuck. Is there any comment from the merch manager? No, okay, good. Well, then we'll skip right to the core of the meeting here tonight. I'll introduce our Vice President, Ron Herron, who will give you the background and introduce you to our speaker and topic for this evening.
You got it, Easy Rider. And for the folks watching on YouTube, next month, or no, 2 months away, get ready for another election. We're going to try to stage that. We'll talk about that at the meeting tomorrow at the museum. In the meantime, ladies and gentlemen, guys and gals, we got the chair himself of University of California, Santa Barbara's physics department. He's on our screen. The Honorable Dr. Claudio Campagnari has talked to us before, back in 2019, before the pandemic hit us. And the man's going to take us into the minuscule and fascinating world of atoms, basic particles, and quantum mechanics tonight. Professor Campagnari is an experimental high-energy physicist, and he's a member of the CMS collaboration from that Large Hadron Collider over at CERN, Switzerland. These days, our guest speaker is pursuing the God particle, also known as the Higgs Boson, and new high-energy physics at short distances. And we're going to let him explain these concepts for the next hour. I want him to be gentle with us. Some of us, just going to hang on. I think he'll do a good job. He was very listenable before. And Claudio is a grad of the University of Sussex in the UK and Yale. Before coming to UCSB in 1994, he was a research associate at the University of Chicago, staff member of the Fermi National Accelerator Laboratory. Title of his speech, Physics at the Large Hadron Collider. Professor Claudio Campagnari, thank you for coming, sir, and talking to us.
Professor, you should be able to share your screen now.
Thank you for having me. It's always nice to come and talk to you guys. It's the second time, but I enjoyed my first go 3 years ago, and it's good to be back. So today I will talk about the physics at the Large Hadron Collider, which is the accelerator where we work. So the Large Hadron Collider is an accelerator, and it has two beams of protons, and it accelerates them to incredibly high energy. The energy is 6,500 giga electron volts per beam. What that means is that if you use the famous E = mc squared equation from Einstein, the energy of a proton at rest is 1 giga electron volt. So each proton has a kinetic energy which is 6,500 times its rest mass. So they're going very, very fast. And then these beams are brought into collision head on. And when two protons in the beam hit each other, all kinds of stuff happens. And their kinetic energy can be used to make new particles, again, using probably the most famous equation in physics, E = mc squared. So I take the energy of this beam, of these protons, they collide, all sorts of stuff comes out, and new particles come out. And we have detectors that are placed around the collision point and that take an electronic picture of the particles coming out. So the Large Hadron Collider is large. It's in a tunnel which is 17 miles long, 300 feet below ground, so you don't see it. So, but that's where it is. This is a picture from an airplane, I guess. And just to orient yourself, over here is Mont Blanc. This is downtown Geneva, Switzerland. This is the airport. So here, this is the runway of the airport. This is where big intercontinental jets can land. So that gives you a sense of the scale. Over here, this is Lake Geneva. The CERN campus is over here, just outside the city. And this is the border between Switzerland and France. So in fact, most of the accelerator is in France. In fact, half of the CERN campus is in France, and one of the cafeterias in Switzerland, and one of the cafeterias is in France. And for a while, you had to bring francs, Swiss francs, and euros to buy your lunch, depending on where you were going. But nowadays, even the cafeteria on the French side takes Swiss francs. Okay. This is a picture of the tunnel. So it's a long tunnel, 17-mile long, and the tunnel is filled with magnets that are used to steer the beams around. And so this is a picture of the tunnel. These are magnets. The magnets are superconducting magnets that are held at liquid helium temperature for about 3 or 4 degrees above absolute zero. So more fun facts about the LHC. Since all the magnets it's the biggest cryogenic system in the world. There are 96 tons of liquid helium in this machine. As I said, there's a 17 miles. The accelerator is 17 miles around. But what's impressive is that the protons have to go through a vacuum pipe, because if they went through air, then they would interact with the molecules in the air, and you would lose the beam very quickly. So there's a 17 miles long vacuum pipe that goes all the way around. And the protons go around 11,000 times a second. They are arranged into bunches, and each bunch of protons collide with another bunch coming the opposite direction every 50 nanoseconds. Now, here's the amazing thing. So you have these bunches of protons going around, and in this 17-mile vacuum pipe, and you have to hit each. They have to hit each other. So you have to, and these bunches have a size of about 50 micrometers, which is like smaller than the size of a human hair. And you have to steer them around so that they hit each other, because if they miss, then nothing happens, and it's not very interesting. So each bunch is 50 micrometer in diameter in cross section, and it's only about an inch long. And there are about 10 to the 11 protons in each bunch. And even though they're bunched so tight into this 50 micron cross section, most of the protons just fly through and nothing happens. But about 20 per bunch hit a proton from the other bunch, they interact, and then all sorts of stuff comes out. And what we do is study the stuff that comes out. So this is an animation of the machine. Everything starts with the hydrogen ball. Okay, so let's play. So hydrogen atoms come out. The electrons are stripped, and so and so you get protons going through, and they go through a series of accelerators that sends them, that increases their energy. The linear accelerator, then the booster, another accelerator from the 60s called the PS, another accelerator from the 80s called the SPS, and then they finally get injected into the tunnel of the LHC, where they get accelerated even higher. And there are 4 experiments arranged around the ring. The biggest ones are Atlas and CMS. We are CMS. We are the good guys. Atlas is the bad guys. They are the competition. And then LHCb and ALICE are smaller experiments. So in fact, our experiment CMS is, so the CERN campus is over here. Our experiment CMS is in the boonies of France, about a good 10 miles away from the campus. Okay. So now this is an interesting plot that is actually pretty depressing for somebody like me who's in this business. What is shown here is on the x-axis is the date. On the horizontal axis is the date. On the vertical axis is the energy of the accelerators. So let's concentrate on these blue points, which are the proton accelerators. And so you see that we made progress, but now things are flattening out, okay? And these are electron accelerators that made progress, and then things are flattening out. And this accelerator called LC, which stands for Linear Collider, which is supposed to, here it says it would start in 2020. This plot is from 10 years ago. Hasn't even happened yet. We are hoping that the Japanese would build it. So one of the problems with this field is that we are hitting a technological wall, and things are becoming too large, too expensive, and we are not on this line where we want to be, where we can explore higher and higher energies. So now the Europeans want to build another accelerator, which is going to be 100 miles around. And it's going, and if they do build it, it will come online in something like 2060. So that's for my children or for my grandchildren. So whatever. But that's a major problem for the field. We're getting to the end of the line with this technology. Okay, so the Compact Muon Solenoid, the CMS, is the experiment that we work with. It's our detector. So in some sense, it's the camera that records what's happening. And there are 2 general purpose detectors, as I said, Atlas and CMS, and we work on CMS. Each detector is designed and it's built and it's operated around the clock by a collaboration of thousands of scientists from all over the world. And it took about 12 years to build CMS. And we started taking data in 2010. So we've been taking data on and off now for 12 years. And there's a plan to keep going for another 20 years of data taking. And I will show you something about the long-term, the history and the long-term plans at the end of this presentation. Okay, it's a massive detector. This is it's basically an onion of detectors that are wrapped around the beam pipe to measure this different, as the particles come out, different detectors measure different things. And there are all these detectors wrapped around the beam pipe. The beam pipe goes like from here through here. So this is like the heart of the detector. And you can see there are many systems. And then you can see which countries are responsible for which system. And to give you a sense of scale, this is a person right here, okay? And it's kind of a joke that it's called compact, the compact muon solenoid, because, but if you looked at the other experiment, Atlas, it's 5 times as big, okay? Except that it's mostly empty. It's mostly empty, whereas we are mostly steel. So we are compact but very heavy. So there are so these numbers are probably a little bit obsolete, but there are about 2,000 PhD physicists working on it, about 1,000 PhD students, 800 engineers, and then technicians, undergraduate students from all over the world. The weight of this thing is 12,500 tons. The overall diameter is 15 meters, and the length is 21 meters. So it's a massive, massive, massive camera. It's the biggest camera you've ever seen in your life. Okay, this is where the collaborators are coming from. There's a very large U.S. contingent. There are a lot of Italians. There are also a lot of Russians, and there are also some Ukrainians. And you can imagine that we're having some issues there that we haven't quite figured out. But this is actually something that CERN is very concerned about. Some friends of mine tell me that CERN, and they're not wrong. CERN was basically built after the Second World War so that the Europeans could have something to do together instead of fighting each other. But now they are fighting. And how to deal with Russia, the Russians, on one side, the Russian scientists, on the other side, which have their own ideas, of course, and then but then also the Russian government and the Russian institutions. It's a completely different. It's a very difficult situation that we're in, but luckily it's not something that I have to worry about sleep and lose nights of sleep over. This is the American institutions that are involved in CMS, and you see that they span the whole country. In California, we have San Diego, Riverside, Caltech, UCLA, Santa Barbara, Lawrence Livermore Laboratory, and UC Davis. Now you can see here that some of our sister UCs are missing, like Berkeley and Santa Cruz, and the reason they are missing is because they are with the competition. They work with the other experiments, so they are the bad guys. Stanford, Berkeley, and Santa Cruz are with Atlas. This is a picture of the detector as it was being assembled. What you're seeing here is a massive coil, a massive magnetic coil. It's also a superconducting magnet. A lot of detectors have to be put inside the coil, and it has a magnetic field of about 4 Tesla. To give you a sense of scale, the magnetic field of an MRI machine is about 1 Tesla, more or less, between 0.5 and 2 Tesla. So this is like 2 or 3 times the magnetic field of an MRI machine, but it is a little bit bigger, and it stores an incredible amount of energy. The equivalent of 0.5 ton of TNT of energy is stored. So when there are accidents and the superconducting coil goes normal, dumping all of that energy is another challenge that has been solved, but it's a challenge. So again, you see, it's humongous. These are technicians and people as the coil was being installed. This is another picture of the detector. Here's some of the detectors that are being sliding into the coil. We worked at UCSB. We worked on building some of these detectors in the early 2000s that are now deep inside. We are now working on some of the electronics for these detectors that are out here. we're building readout electronics to be able to read out the signals that come out of the detectors. This is another picture with the two halves of the detector. So this is one half, this is the other half. The beam pipe is not here right now, but it would be slit through here. And once, and at some point, the detector gets closed. So these two massive pieces move together and close the detector. And again, for scale, here's a person down here. And all of this happens 100 meters underground. So here's another picture of what happens when we have a collision. So this is the detect. Actually, this is actually a picture or an animation of an actual collision from 2010. You can see it here. So let's see. So this is the detector. Now it's rotating, and now you can imagine the protons that are coming in this way. They go to these detectors, and then they hit each other, and then all sorts of stuff comes out. And you see what you're seeing here are tracks that are bending. These are charged particles. The magnetic field, they bend in a magnetic field. So that's why there is a big magnet, because we measure the energy of the particles by how much they bend. The more energetic they are, the straighter they go. So we measure their energy by measuring how much they bend. So this is a picture of what's going on. Okay. All right. So what was this? This was the same. Okay. So what do we do? What is the science that we do? We're doing particle physics, which is the study of the building blocks of matter and their interactions. So you have atoms, and atoms have a size of about 10 to the minus 8 centimeters. Okay, and an atom has a nucleus inside and some electrons that are flying around. So now if you zoom into the nucleus is just takes up a tiny fraction of the atom. The atom is 10 to the minus 8 centimeter. The nucleus is about 10 to the minus 12 centimeter. And then if you zoom into the nucleus, you'll find protons and neutrons, which have a size of about 1/10 of the size of the nucleus. Well, it depends on the nucleus, but roughly. And then if you zoom into the proton and the neutrons, you find quarks. And as far as we can tell, quarks have no size, okay? So what we can say is that if they do have a size, the size is smaller than 1,000 the size, about 1,000 the size of a proton. And the electrons themselves are also, as far as we know, they don't have size. And they also, if they do have a size, their radius is also of the same order, at least smaller than 10 to the minus 16 centimeter. So this is what we do. We study the interactions of quarks and the interactions of quarks with electrons and things like that. And in order to study this, we have something called the standard model of particle interactions. And so we talked about the quarks, the up and the down quarks. Those are the quarks that make up the proton. And then there are the electrons that we all know about. That's what's running into our wires and give us electricity. And then we have the photon, which is the particle which is associated with electricity and magnetism, and so light and X-rays, radio waves. Those are all photons. So we have the up and down quarks that make up the protons and the neutrons. The protons and the neutrons and the electrons make up atoms and molecules. And you would think that that's it, you're done. Well, not so much, because you need something that holds the quarks together to make a nucleus, to make a proton. And you have some particles which are called gluons. And then gluon comes from glue. So it's something that glues together quarks. These are particles. And these are the particles that keep the quarks inside the proton and the neutron. Okay. Are we done? No. We're not done because there are also neutrinos that were discovered in the 1930s, which you can see in some radioactive decays. And then there are these particles called the W boson and the Z boson, which are associated with the weak interaction, which is the interaction that is responsible for this radioactive decay of with neutrinos, which is called beta decay. So some nuclei decay into neutrinos and electrons, and the particles that help this interaction go are the W and the Z. Okay, this looks good. We're done. No, we're not done, because everything gets replicated twice, two times more. And so there are more quarks, the charm and the strange, the top and the bottom, and there are more neutrinos, and there's other particles. This particle is called the muon. It's just like an electron, only it's much heavier than the electron, and the tau is even heavier. So this structure of matter, the normal matter that we see is in atoms, is the up-down quarks, so the protons and the neutrons and the electron and the photons. But this pattern is repeated 3 times. Why is it repeated 3 times? Nobody really knows. It's a mystery, and we're pretty sure that it's not repeated a 4th time. If it's repeated a 4th time, the fourth copy is quite different from the first, the second, and the third. We call this generation. The first generation is here, the second generation, and the third generation. Okay, so, and another mystery is that these generations have the same properties, except that the masses are wildly different. So these are the masses of the first generation particles. This is mass on this on the vertical axis, but it's a logarithmic scale. So each tick here goes up by a factor of 10. Then this is the second generation, and then this is the third generation. So, for example, the top quark has a mass in these units of about 200, whereas the electron has a mass in this unit of 0.0005. Okay, why do we have this hierarchy in masses? Why are the masses so different? We have no idea. Okay, if you can figure it out, you can book your trip to Stockholm and pick up your Nobel Prize. Okay. And then the neutrinos are even weirder. For a long time, we thought that the neutrino had 0 mass. And then there was an experiment in a chlorine mine, in a mine in South Dakota, where a guy named Ray Davis put a big vat of cleaning fluid, basically chlorine, and he saw. And he was looking for neutrinos from the sun, and he saw that so when a neutrino from the sun comes, it can hit a chlorine atom and turns into an argon atom. So he would put this big vat of cleaning fluid full of chlorine into this mine, and then once a couple of months, he would take it out and count the argon atoms coming out. And it didn't quite work out. The number of argon atoms that was coming out was not what one would expect from the number of neutrinos that were coming from the sun. And one of the explanations was, well, maybe neutrinos have mass, and for some technical reason that would cause this discrepancy. I remember I was a graduate student, and I just thought, well, it's a miracle that they can figure out how many neutrinos are coming from the sun within a factor of 2. So I'm not going to pay attention. 0 is a very nice number. I like 0. Well, I was totally wrong, because the result was correct. And now we know that neutrino have masses, and their masses are even tinier. This is 10 to the minus 11 in this scale, whereas this is 10 to the minus 3. It's another huge mystery why neutrinos have mass, and why do they have a mass that is so different, so much smaller than any other particle. So the standard model, it's beautiful. You can just write, so this is the equation of the world, okay? Well, except for gravity, because we don't understand gravity with quantum mechanics. But this, you have this equation, which is really, looks very nice. You can put it on a t-shirt. It's a very cool t-shirt. You can put it on your coffee mug. It looks very, very nice, very, very simple. But it looks very, very simple because all of these symbols are really abbreviations for something more complicated. And the way it really looks like it's this. And even these symbols are abbreviation for things that are more complicated. So I like to scare my students by giving them this equation and asking them to explain every term and what it means. Okay, so we're doing particle physics and we have questions. So these are the questions of particle physics. A big question is, we know that there is antimatter. And when the Big Bang happened, we think that as much matter as antimatter was created in this Big Bang. And when you take a piece of matter and you hit it against a piece of antimatter, they annihilate each other, and all you get out is light. Okay, effectively. So, but some matter survived the Big Bang. I mean, our world is made of matter, and there's no antimatter around that we can see. So our world is made of matter, not antimatter. So in this primordial soup, when matter and antimatter were annihilating each other, there was some process that caused a little bit of matter to survive, and it is that matter that now makes up the planets, the stars, the plants, you, us, etc. So where is this? What's this asymmetry? Where is it coming from? We have in our theory an asymmetry between matter and antimatter that we've actually measured in the laboratory, but it's not nearly enough for the development of the universe. So there's something else that we don't understand. Now you guys are interested in astronomy, so you know about dark matter. So if you look at how the galaxies, our stars move inside the galaxies, it looks like they move under the influence of some matter that we don't see. That's dark matter. And in fact, that dark matter makes up a big fraction of the matter budget of the universe. And in the last 20 years, there have been some measurements that have now proven that there's also something else that permeates space called dark energy. So dark matter and dark energy, we have no idea what it is. I mentioned a few minutes ago this business of the generations. This stuff here, why are there three? No idea. We don't know. Why are the masses what they are, and why are they so different from one generation to the other? How do particles get their mass? It turns out that this beautiful equation doesn't work unless everything has mass equals 0. Well, mass equals 0 doesn't make sense, obviously. And so what you find is that in order to give mass to the particles, you need some special mechanism that can give mass to the particles. So how do particles get their masses? I told you that as far as we know, quarks and leptons have no size. They're not made of anything. Well, is that really true? You know, if we were to look deeper, will we find even smaller pieces inside? It's like the Russian dolls. Are we at the end? Are we at the end of the smallest Russian doll, or is there are more Russian dolls inside the Russian dolls that we have? Okay. And then, of course, what about gravity? You know, you're interested in astronomy. You know that all the motion of the planets is driven by gravity, et cetera, et cetera. It's all very good, but gravity and quantum mechanics don't get along. We do not know how to marry gravity with quantum mechanics, and so for the physics of black holes, for example, is still something that we don't understand. So what is the job of the LHC? So these are the big pictures. And so what is the job of the LHC? It was built with two main goals in mind. The first goal was to address the question of mass. As I said, mass must be generated through some kind of interaction. And the second question was to try to shed some light in any of the other questions that are here. By going to higher energy, let's see, and shorter distances, let's see what we can see, and see if we can answer any of these questions. So let's talk about mass first. One solution, not the only solution to the mass question, was put forward by Mr. Higgs in the 1960s, and Mr. Higgs and others, to be honest. And they imagined that empty space would be permeated by some field called the Higgs field. You can think about, sounds like a weird concept, but if you think about it, the fact that space, that there are magnetic fields there could be magnetic fields in space is not something that is out of our everyday experience, right? You can use a magnet and there's a magnetic field in space. Now imagine that all over space, there's this new field called the Higgs field, and that particles would get their masses. And what is mass? Mass is inertia, is difficulty changing its their motion by interacting with this field as they move, okay? And then this field would result in the existence of a new particle called the Higgs boson. Just like the fact that there's electric field and magnetic field means that there's a new particle called the photon, okay? So if there is a Higgs field all over space, and particles traveling through space interact with the Higgs field and acquire mass, then there's a manifestation of this Higgs field is actually a particle itself called the Higgs boson. This was one of the solutions to the mass questions when the LHC was turned on, and it appears to be the correct solution, because 10 years ago now, the Higgs boson became very popular because we actually found this particle at the CMS and at Atlas. It was a triumph for particle physics. It was a very exciting moment for all of us who have spent many, many years working on these things. So now that we have found the Higgs boson, we have a two-pronged program at the LHC. On one side, now that we have the Higgs boson, we have discovered it, but now we're going to study it to death. It's a weird particle in many, many ways. And does it really behave like the theory predict, or does it behave in a different way that might teach us something besides what we think the Higgs boson is? And then the second part of the program, in layman's term, is look for new stuff, right? You are exploring a new energy regime where nobody has ever looked before. Is there anything new out there? So studying the Higgs boson. So 10 years ago, we discovered it. We've been taking data, we've been analyzing data, and we've been measuring various properties of the Higgs boson. And I just want to give you a flavor for it. This is a plot where here's on the horizontal axis is the mass of particles. And on the vertical axis is the strength of the interaction with the Higgs boson. So how strongly do they interact with the Higgs boson? And I told you that mass has something to do with the interaction with the Higgs field. So you expect that the more massive the particle, the stronger its interaction would be with the Higgs boson. And in fact, the theory predicts that everything should be on this blue line. And we made measurement, not all the particles, but many of them, and they line up. They line up. The strength of the interaction between the Higgs boson and the top quark is about what you expect. It's not that these are not super precise measurements, a measurement that with a precision of about 10% each, but is indicating that it looks and it smells like a Higgs boson should. But we want to go deeper. We want to make measurements that are much more precise than this to see if it really works. These are other measurements of the Higgs boson. This is very technical, and it doesn't really matter what it is, but basically what's measured is how it's produced with respect to how you expect it to be produced. So if everything was according to theory, all of these data points would line up on this line of 1. And you see that they do, but the error bars are still large, okay? And so a major part of our program is to make this error bar smaller, this error bar smaller, to really test what does this weird particle really look like. And then there's the next Higgs frontier, the next holy grail in Higgs physics, is to study the production of 2 Higgs bosons at the same time. And the production of 2 Higgs bosons at the same time has something to do with how the Higgs interacts with itself, okay? And this is a very important test of the theory, because the theory tells us how it should be interact with it, how the Higgs boson should be interact with itself, and we have no measurement whatsoever. So we want to measure that. It's very difficult to measure. We have not seen any indication that it exists because it's very rare, and it requires much more data, which we will be collecting over the next 10 years or so. But then the Higgs boson is a confusing and weird animal. So if you look at the mass of, so you measure the mass of this particle. So this is the mass of the Higgs. So there's an equation here. The mass of the Higgs squared is equals to some parameter, let's call it m0 squared, plus or minus some correction. This is what you measure. This is what you put into the equation that goes on the coffee mug. You put a number in, and then there's a correction which comes from quantum mechanics. And the correction, this is going to be the only real equation that I show, okay? So I apologize, I just want to show one equation. The correction is given by some integral of some function of energy integrated from 0 energy to infinity. Okay, this is high school calculus, okay? I apologize. All right. So the correction is this integral here. So this function looks like this. It doesn't matter what it looks like, but the weird thing is that if you keep calculating, this is how it looks. It keeps growing. And now, if you don't remember high school calculus, I tell you that an integral from 0 to infinity of some function like this is equal to the area under the green curve. And now if this thing goes on forever, the area is infinite. So that's not good. So what we think is that at some point, some new phenomenon, a very high energy turns on, and then this curve somehow turns over. And so this area is finite, okay? Now, if I just do this, if I just draw this triangle, now the area of this triangle, now this is the area of the triangle is the base multiplied by the height divided by 2. So the base is the energy where something happens. The height is this number A times E, so E times E nu, and then 1/2. So the area is 1/2, some number, doesn't matter what it is, some number can be something between 1 and 10 or 1 and 100, it doesn't matter, but it goes like the energy of new stuff to the second power. So, okay, so remember, the mass that we measure is the mass that we put in the equation minus the correction. And so it looks like this. The mass that we put in squared minus this correction here. So now the question is, what can E nu be? What can be this new, where does this thing stop growing, right? So one thing that we know is that at some point, our theory breaks down because quantum gravity becomes important. We have no idea how to calculate anything in quantum gravity, but we know where quantum gravity becomes important. It's at a new energy, which is 10 to the 19. Okay? So imagine that there's nothing between where we are now, which is around here at the LHC, and quantum gravity. Then we find that the mass of the Higgs boson, which is 125 GeV squared, so that's a unit, doesn't matter, is equal to whatever, some number that we put into the equation, minus some number that is something like 10 to the 19 GeV squared. Okay, now look at this carefully. I have to get 125 squared by taking some number and subtracting 10 to the 19 squared. In order to do that, I have to take this quantity here, m0, that I put into the equation, and I have to fine tune it to 17 decimal places for this to work. All right? So how crazy is this? So here's an analogy. Imagine that you have an accountant that looks at the money that the United States government puts out in 2022. Actually, I made this slide before the pandemic, so I think now it's much more than $3.8 trillion, but okay, let's pretend that it's only 3.8 trillions. And actually, the accountant is a very precise guy, and he says it's 3,867,987,967,321.67. Okay, that's what the accounting on the expense tells us. And then there's another accountant on the revenue side that counts all the tax revenue. Okay, let's pretend that the tax revenues more or less balance the budget. We know they don't, but let's pretend. And he counts them, and he gets 3,867,987,967,321.66. So the balance is 1 cent. Okay, so now you can say, well, okay, this was an accident, that the budget is balanced to 1 cent out of 4 trillion, or you have to imagine that there's some mechanism that ties the expenses and the revenue together so that they have to be tied together. There must be something, some new accounting, some new something that ties them together. Otherwise, it doesn't happen. This is what we call the problem of naturalness. It's natural to expect that there is some mechanism that prevents something like this to happening. In other words, there's something. So what we want is that the new physics would turn on around here, around where we are, so that then we don't have to fine tune these numbers to a part per 10 to the 19 in order for it to work. And so this is called naturalism. It is natural to expect that there should be new physics to be discovered at the energy probe by the LHC, if the Higgs boson is there, which it is there. And this new physics should be around 1000 GeV, which are the energies probed by the LHC. Okay, this is the naturalness concept. Now, before the LHC turned on, people were convinced that we would find this new physics, no problem. It would just stare us in the face. We would find the new physics within 20 minutes of running. And the problem would not be so much that we would not find the new physics, but to actually figure out what the new physics was. So some people, theorists, organized what they call the LHC Olympics, okay, where they gave various teams of physicists fake data with some fake new physics model, and they said, analyze it and tell me if you can tell what it is. So they called this the inverse problem, and people thought seriously that this was going to be the big issue of the LHC. we find some new physics. It's going to be hard to figure out what it is. Let's do some Olympics. Let's do some warm up. Let's try to understand how we're going to do this. Well, the problem is that it has not turned out that way at all. What is this? This is a laundry list of possible new physics processes. It doesn't matter what they are. And what's shown here in yellow is the ranges of masses that have been excluded. So this is 1 TeV, the magical 1 TeV. So there's a lot, everything that we haven't found anything, and we have excluded a lot of stuff at around 1 TeV. Okay. When people were talking about the LHC 15 years ago, before it turned on, this was called the nightmare scenario. The nightmare scenario is that we find the Higgs and we find nothing else. And if that's the case, we're going to be really confused, because we know that there's something to be found, but we can't find it. That's the nightmare scenario. And it looks like we are close to the nightmare scenario, not quite, but we're very close to this nightmare scenario where we don't know, we have not found what we were hoping to be able to find. Now, to be fair, not everyone believes in naturalness. In particular, there's this German physicist, Sabine Ossenfelder, who actually used to be a postdoc here at UCSB 15 years ago, who actually wrote a book called Lost in Math, and the subtitle is How Beauty Leads Physics Astray. She doesn't believe in that this argument about naturalness make any sense. She thinks that, yeah, it's probably an accident, so what? And actually last week she published an opinion in the Guardian in England. No one in physics dare say so, but the race to invent new particle is pointless, which caused a little bit of consternation in the community. And this is a funny cartoon. There's this naturalness, 1988 to 2017, killed by ugly facts. Okay, all right. So that's Sabine. But what is the lessons, in my view, from our experience with searching for new stuff? The main lessons is that the conventional prejudices of what the new physics should be have failed. The theorists, I tell my theorist friends, you guys don't know what you're talking about, okay? And this is a good cartoon. This is where you lost your wallet? No, I lost it in the park, but this is where the light is, okay? So whether one believes in naturalness or not, as experimenters, it is our job to continue to explore. Whatever the theorists say, because they've amply demonstrated that they don't know what they're talking about, and whatever the philosophers say about whether naturalness is a good idea or a bad idea. So what we're doing now is looking for things that we haven't looked before. We're going away from the lamppost. We're going away from looking for conventional things. So we're looking for unconventional signatures where we did not look before, or inventing new techniques that are more sophisticated and where we may be able to uncover something new. And the other thing that we're doing is that we're making precision measurements. So precision measurement of the properties of the Higgs boson, but also precision measurements of other physics. And in fact, there are some hints around that some things are not so great. So this is over here. This is a result that actually came out recently from an older experiment that reanalyzed their data that made a little bit of a splash. The latest measurement of the W boson digs at the most important theory in particle physics. So Science magazine asked me and one of my colleagues at CERN to write a little article for the non-expert to explain what we're seeing. So there are some hints here. There are also some other hints here. There's some of these precision measurements that are not quite matching up what we expect these measurements to be according to these beautiful equations that fit on the T-shirt or the mug. So there are some hints, and we just need to, I think we just need to dig deeper. Now, what does the LHC look like? This is the LHC planning. So this is the year. This plot is pre-pandemic, so everything has shifted by a year or two. Where it says LS, this means long shutdown, where the accelerator shutdowns, both to save money and also in terms of power bills, but also to do upgrades. In fact, last week I got a communication from CERN that they're going to extend the shutdowns in the next year or two because of the energy crisis in Europe. They need to do their share in order to bring down the energy consumption of Europe, given what's going on now. Okay, but the accelerator started running in 2010 and took data until 2018. On these blue lines is the amount of data that we have taken. Now we started again this year, so this shifted by 1 year. We started again this year, and it's going to go a little bit up. Then there's going to be another shutdown for a major upgrade, and then then the amount of data is going to rise faster than it has occurred over here. Basically, the intensity of the beams is going to go up. So in some units, whatever the units are, we have about 160 units of data that we've taken until 2018, and okay, they want to run until 2040, when I will be retired, long retired, and they're going to reach 4,000. Okay, so now we have 160. So we are going to take more and more data, and we are going to do also upgrades to the detector to improve their capabilities. So in fact, at UCSB, we're working on various upgrades for the detector. We're building some electronics to upgrade the data acquisition system so that it can handle higher data rates. This is the clean room where we're actually building some of the detectors that are going to go in. This is a picture that was taken this summer. These are a bunch of students, undergraduates and graduate students from UCSB that were at CERN. In fact, on the side, we are installing a little experiment to do some of the searches for weird things that the big detector cannot do. So it's a detector that is being installed now at CERN. So these are our students here. We are involved in designing a brand new detector to add capabilities, and here you can see some silicon sensor bonded to, well, for now, to mechanical fakes where the actual electronics will go. Okay, so let me finish. We have taken 10 years of data at the LHC, and what we have done is we have discovered the Higgs boson. We have measured many of its properties at the 10% level, and we have made many new measurements of standard physics processes in the standard model, looking for effects that we do not understand. One of the big advancements is that we have realized that the conventional theoretical wisdom of what lies beyond the standard model was wrong, was very likely wrong. So the whole field is confused. People are looking for new ideas. The theorists are in the dark trying to figure out these new ideas. But we as experimentalists, we just go and look at what we can find. Only 3% of the ultimate amount of data has been collected. A major emphasis in the future will be to carefully study the Higgs boson. We're going to study it as well and as carefully as we possibly can, because the properties of this boson may very well be the key to point us in the right direction to understand many of the questions that I've listed earlier on in the talk. And I will conclude with this with thanking you for inviting me. And if there are any questions, I'd be happy to take them.
Very good.
Yes, I have a question.
Yes.
What is the detector made out of, and how do you actually detect a particle? Can you only detect charged particles?
No, we have many. Okay, we have many detector systems. So inside here we have something called the tracker, which is basically is made out of silicon sensors. Imagine many sensors, so many camera sensors.
Yeah.
200 square meters of them. And so when a particle goes through, it leaves a little hit on the pixel, and then we read the pixel. And then from the pattern of pixels, we end up. Do I have a picture of that? We end up reconstructing the trajectory of charged particles. Then outside the tracker, we have what we call calorimeters. So this is the crystal electromagnetic calorimeter. These are crystals of BGO when a photon goes into the crystal, it showers and gives a big light spike. So then we light of those. Then we have some particles called muons that don't interact and go all the way through, and we detect them into these outside detectors. So it's a combination of many pieces of detectors that work together, and then at the end of the day we put it all together to try to understand what went on in the event. Okay.
Now does the tau and the mu particle, they're the same sizeless thing as the electron?
Well, if we have a new so that's a very good question. So if we have a new particle, new particles, they in the most obvious way, they will decay into particles that we know.
Yeah, I meant mu, not mu.
There are some crazy theories. So, for example, these little detectors that we've designed mostly in Santa Barbara with some friends from other institutions. Where is it? Can you still see my stuff?
No, we're looking at the whole motley crew.
All right.
You need to reshare.
Okay, share again. Can you see it again?
Yes.
Here we are.
So this picture of the students here. So what we've designed. Imagine that the new particle has an electric charge, but has very small electric charge. And there are some crazy theories that can give you particles like that. Particles with very small electric charge would not be seen in the detector, because the detector is designed to see charged particles with the charge 1 in unit of electron charge. So if the charge is 10 to the minus 3, we wouldn't see it, and it would go through, it would exit the detector, travels through the rock, and then it would end up in this tunnel, and we are instrumenting this tunnel with some detectors actually to see these particles. So this is
charge.
Yes, particles with very small charge. So this is a human scale detector that we've built a lot of it here in Santa Barbara. We shipped it, and was installed mostly this summer by these kids, and we're starting to take data now.
Looks like you have to put a box to check for if people are claustrophobic to get on this team.
Yeah, I mean, this was a drainage gallery that they built to get the water out when they dug the cavern where the detector is, and it's behind 20 meters of rock away from the detector. So these guys are here, and they just installed this detector over the summer.
Okay.
Chuck McPartland, do you have a question?
No, we're happy campers.
I've got a question.
Okay.
The question is, I'm confused, about fields. A particle has mass; it's equivalent to an energy. but what does the field mean? What does that mean? The Higgs field, electromagnetic field.
Yeah, that's not such an easy question to answer without a lot of math. But you know, magnetic fields and electric fields don't bother you, right?
Well, they might interact with atoms
Yeah,
electronically or something.
magnetic field interacts. You know, if you have a little bar magnet, the magnetic field interacts with the bar magnet. At the fundamental level, it interacts with the electrons and the nuclei of the material. So in the theory of fields, when you take the theory of fields, the electric fields and magnetic fields that that kids learn in high school, and you marry it with quantum mechanics, you get a new theory called quantum field theory. And for each field, there is a set of particles associated with it. Now, my theoretical colleagues tells me that you shouldn't even use the word particles. A particle is just an excitation of the field, but that's even too esoteric for me.
How about Chrissy Cook? You have a question?
No, but it was a fascinating talk. I mean, I just love the idea of everything we ever do is probably wrong. That's so frustrating and also so compelling.
Yeah, we don't hear that a lot, do we?
There's a
But
couple
it's
of
not
questions
the
here.
We had questions,
Sorry.
didn't we, during the talk?
So Tessa's asking, might any of the anomalies caused by the behavior and dimensions we cannot currently detect? So, you know, extra dimensions in space that are hiding things.
Yes, why not? Sure.
Good.
I mean, so the idea is, that there are all these crazy ideas out there, including extra dimensions and whatnot, and they may be right. But what we want to, so once we see something that does not fit the theory that we have now, then people can propose new theories to make it fit. And so, and the space of new theories that you can make is infinite. So, I mean, actually, we have a word for this. We call it ambulance chasing. Every time that there is a new effect, we think that there's something new that maybe a statistical fluke or something, and it gets out within 3 weeks. You get 100 papers proposing a solution, and that's what we call ambulance chasing. In fact, we're going through this process right now. There's one group from Zurich in our experiment that is seeing something weird, and it was presented to the collaboration 3 weeks ago. And some of my friends that were paying more attention than I was wrote to me and said, Claudio, connect to the meeting. I know it's going to be at 2 a.m, but connect to the meeting and listen to it because you need to listen to it. So I listened to it, and I have a big mouth. I cannot keep my mouth shut. And it looked pretty fishy to me. And so I sort of threw out some challenges. And so now the collaboration decided that they needed a task force to figure out what the heck is going on, and they put me in charge of the task force. So now I have a meeting every Wednesday and every Friday at 5 a.m. Just serves me right for not keeping my mouth shut.
Do you happen to know?
And I'm gonna try to figure out whether what this group from Zurich is seeing makes any sense. And if it doesn't make any sense, well, then we kill it, and then that's it. And if it does make sense, we'll publish it, and then the ambulance chasing is going to start. But in this field, you cannot keep a rumor down. I mean, it's worse. It's worse than Washington, than the government, right? So the leaks are everywhere. And in fact, one of the theorists at UCSB that is not involved in CMS not only knew about the rumor, but even knew that I was in charge of trying to figure out whether it was real or not. So I'm sure that people are preparing papers, and if we do come out with some anomaly, the ambulance chasing will start. So that's what happens.
Well, it sounds like a lot of excitement, a lot of fun.
In fact, we're doing some ambulance chasing in my group also. There's another effect that is smaller but looks tantalizing, and we said, well, if that is right, then we should also, if that thing is right, then we should also see this other thing. And so right now we're chasing this other thing to see if it's there. So that's kind of fun.
Yeah.
That Hadron uses so much power that it has to be shut down for months at a time.
Well, it's always shut down. So it's interesting. When I was working at Fermilab near Chicago, the accelerator was always shut down during the summer because of air conditioning. I mean, because the power in the Midwest, power requirements in the Midwest for electricity go up in the summer for air conditioning, so the price of electricity goes up.
Yep, right.
In France, it's the opposite. They don't have a lot of air conditioning, but they have heat. They need heat, and so the cost of electricity goes up in the winter. So we usually shut down in November and then come back in March. We also take that time to do all sorts of maintenance.
You have any idea what the electric bill is for the Hadron CERN Collider?
No, I don't, but I don't know.
Who pays it? I guess whoever's using it.
Well, it's paid by CERN, and CERN has a budget of about I think it's about $1.5 billion a year.
Wow.
That's the CERN budget, and it's funded by European countries. The United States is not a member state of the CERN organization. But we contribute in kind. We contribute by building pieces of the accelerator and pieces of the detector and things like that. So, for example, this upgrade the upgrade of the detector that is going on over here, the American cost is about 200 million. Of various pieces. Now, given that the dollar is so much stronger than the Swiss franc, and the euro, maybe the price in dollars is going to go down. But whenever we do an upgrade and we have to build some detector, I mean, if you look at these detectors right here. Okay, so you see that all of these components are built from different countries, right? Collaborating with each other, and there's always negotiation of how much money and manpower will each country contribute to the construction. And I think the United States also contributes a set amount to the operation of the detector and of the accelerator, in order to have access to the science.
But physicists from around the world can book time using the collider, just like an astronomer would.
No, it's very different. So the collider runs, takes data. We all work together to take the data, to make sure that the data. I mean, there's a lot of work goes on in taking the data. There's a lot of work that goes on in making sure that the data makes sense, that things are not broken, that people are carrying cell phones 24/7 to come in and fix things as they go bad. But then the data is available to everybody, and we have an organization that does different. So we have an organization where we are divided in order to do the science into different science groups, depending on what you want, what people are interested in. But then every scientific result that comes out is a paper that is signed by everybody. So I end up, when I have to give my CV to UCSB to get a salary raise, it's kind of embarrassing because I have so many publications that I don't even know how to count. There are 150 publications every year, and each publication has 2,000 names. So
you got good tenure, do you, Claudio?
yeah, well, I have to explain to the committees that are made of people that are not in the field, or why I have 2,000 papers and why each one of my papers has 2,000 names on it. And so,
have you produced a paper yet that has more names on the author list than lines of content?
oh yeah, in fact, now let me show you something else. Just an example. So I'm going to pick up a random paper, then I'm going to show it. Stop sharing and share something else. Okay, can you see it?
Yeah.
This is a paper, and it says A. Tumasayan et al. CMS collaboration. And then it says full author list given at the end of the paper. So this is the paper. This is actually a paper that I wrote personally. But and then at the bottom of the paper, here comes the Here comes the list of authors. Okay, it's kind of ridiculous, but that's the way it is.
Wow.
I think Chuck has that, doesn't he? He passed it around. Don't we subscribe to this? Wow.
Yeah.
Review letters.
Yeah. Well, we'd love to have you add to your collection our newsletter, which will come out in the beginning of March, or where am I? November. I'm in the wrong side of the year. Listen, yeah, we're going to say goodbye to everybody, but
well, Ron, I have one more question if I want to ask.
Yeah.
Is there any chance that astrophysics collisions of black holes and things will generate any information that'd be helpful for the particle physics side of things?
Yeah, you know, that's an interesting question. The two fields have something in common, right? The very small and the very large. You think that they don't talk to each other, but actually there's a lot in common. Now, the collision of black holes and that kind of astrophysics might shed some light on quantum gravity, not so much on particle physics, but dark matter is a common issue in astrophysics as well as particle physics. So a lot of the evidence, I mean, all of the evidence for dark matter comes from astrophysics. Now, we think, and there are models, there are particle physics models that are trying to explain the astrophysics observation of dark matter, the amount of dark matter, et cetera, et cetera. So the two fields touch each other, right? And there are also on the experimental sides, there are some experiments in space looking for gamma rays that are trying to see the signature of dark matter. So there is certainly there is an intellectual connection. There is also in some cases there is also a technical connection. Many of my friends that started in particle physics have become astrophysicists, and they're working on new telescopes and in particular new technologies for telescopes, and also the data handling. I mean, we are experts in data handling. we have so much data that we could drown in data and in data analysis. So there is a connection. It's not super strong, but it's strong.
But you did find the Higgs, and old man Higgs, I guess, took the award, right? But you guys are the ones that found it or proved it.
Yeah, but who cares?
I didn't know it had been 10 years. Claudio, you did good. We are just enthralled, and thank you very much. And we'd love to have you back again with an update in a year or two if you are still there and available. And
Well, thank you very much. It's always a pleasure to come and talk to you guys.
well, thank you on behalf of the club. Before I throw it back to Jerry to close things out, Rory Bentley is the name of the other bright young grad student at UCLA we're going to have on board next month, November 4th. First Friday, Rory will take us deep into the deadly center of the Milky Way. Mr. President,
Okay,
thank
thank you
you.
very much, Claudio. It was very informative. Excellent talk.
Yeah.
Okay, bye-bye.
Thank you.
Appreciate it.
Bye.
See you next month.
Bye, everybody.